I'm delighted to be here. I don't know if you guys know how delighted I am to be here, because about 22 years ago, when I started coming to this program, I was sitting in this exact hall, sitting where you were, wondering if it was ever possible that I would know enough stuff to stand up here and be where I am now. So if you're sitting there wondering, will you ever know enough stuff to stand up here? I have proof that the answer is yes. Okay, so I'm going to give an introduction to machine learning that assumes you know nothing. Okay, assumes you know math, but doesn't assume you know any machine learning. All right, so in machine learning, and I know Leslie covered some of this yesterday, so it's somewhat of a repeat, but hopefully it'll catch on the second time around. So in machine learning, the goal is to teach computers to learn by example. Okay, so I want you to think about the example of self-driving cars, right? Self-driving cars is like kind of a key application for machine learning right now. So you have a camera that's aimed at the front, looking around, front of the car, it's aiming outward, and it has to figure out what the objects are that are in the scene. And it needs to do this very carefully. For example, if there is a deer in the image, the self-driving car needs to know about that deer, because deers do unpredictable things, and the car needs to be very careful if there's a deer anywhere. So I want you to think about how we would design a classifier for a deer. So it's a piece of code. Okay, I'm going to draw a database anyway. We're going to draw a piece of code, and we need a whole bunch of labeled data for identifying here. So we have a whole bunch of images. There's my database here. Let's see if I can play this here. So you can mow all day, and I'm still going to be drawing this database. I'm kidding. Okay, so here's another deer, and then I have some other images that are not here. To the extent of my artistic ability there. Okay, and so the idea is that, if there's another image, it's a new image that the camera takes. I've never seen this before, it's not in my database. And I have to figure out whether or not it's a deer. Okay, that's the goal. And even though I've never seen this before, if I've designed this recognition system well, then it should be able to kind of see the patterns in the database well enough that it can sort of identify the difference between a deer and a non-deer. Okay, so what it's doing is pattern recognition. It's going to find the patterns in the database. It will allow you to identify what is not. Okay, so machine learning is pattern recognition. Machine learning is part of artificial intelligence. There is no real intelligence. It's just pattern recognition. It's just looking for patterns. Okay, so I know people get all excited about machine learning and they go, oh, it's artificial intelligence, it's patterns, it's learning something. Can it be smarter than humans? There's no real intelligence here. It's just looking for patterns. Okay, now I want you to get into the mode of thinking about everything as a vector. Okay, so I'm going to start with images, right? And so I want you to think of images as vectors. So how is it that an image can be a vector? Okay, so an image, actually, if you think about it, is, you have your image, and each pixel is represented by a set of red, green, blue values. So maybe the values look like this, 0.9, 0.8, I don't know, whatever it is. Okay, so every pixel in that image is represented by 3 numbers. And so if you just stack all these numbers together, you just get a giant vector. Okay, so images are vectors, but I want you to get the idea that anything can be represented as a vector. Well, almost anything. I mean, it's not true that everything gets represented as vectors, but most of the time in machine learning, we do represent things as vectors. So let's think about a medical patient So the medical patient is sick. And so what we're going to measure about that patient is a set of numbers. So we measure maybe the blood pressure, the weight, whether or not they take blood thinners. So one, if they take blood thinners, and so on and so forth. Okay. And then we might try to predict, for instance, whether the person will have a heart attack. So here's my label, which is whether or not they had a heart attack. And so these are called features over here. These numbers, this vector of numbers that represents the object here. These are called features. They also have other names. So if you're a statistician, you'll call them covariates. So you might accidentally hear me saying covariates. They're also called explanatory variables, independent variables, predictors. That's the name for this type of thing. And you're going to take, this is X, and that's why you're going to predict Y given X. Okay, cool. So any questions about the setup so far? Okay. All right, so let's talk about let's go for like a two-dimensional example. Let's say, and I'm going to do 2 dimensions because I can plot things in 2 dimensions, right? So I'll just write, I can plot 2D vectors. So I have my person, this is my medical patient here, who, is had a heart attack, okay? So then I can just write down their blood pressure and their weight. So those are the only 2 features I'm going to use about these people. So I'm going to construct a 2-dimensional classification problem. Here's another person who maybe doesn't get a heart attack. Don't worry, the examples get happier later. Okay, so this is X and this is Y. And then I can take my whole database and plot the whole thing in 2 dimensions. I can just put blood pressure on this axis, and I can put weight on this axis. And I can have, maybe the people who have higher weight and higher blood pressure are more likely to get a heart attack. Okay, so those are the positive examples. And the negative examples, maybe the people, to be honest, it's all mixed up. It's going to be all mixed up. But right now I'm pretending that people who have very high weight and very high blood pressure are positive, and then people who don't are negative. And then our goal in classification, oh, I ran out of page. I'm going to just copy this here. Much easier than a chalkboard, right? Okay, so here's, by the way, here's my patient with 140 and 160. So that was like this guy was like the example I gave a minute ago. Okay, so this is my whole database. And in classification, which is a kind of the standard problem that everybody starts with in machine learning, is classification. My goal is to create a function f of x, okay, so that the sign of that function equals the label y for that x, okay? So that's my goal, is to create a function whose sign agrees with the labels. So if I draw this function, maybe something like this. This is typically the way we draw the function. And this is f of x equals 0. That's the decision boundary. And then above this point, f of x is positive. So its sign agrees with the labels. And then below this point, f of x is negative. Okay. So just to repeat that here. These are positive predictions, and they agree with the label, so that's good. These are negative predictions because the sign of f of x is negative. Those agree with the predictions, that's good. This is the decision boundary where f of x equals 0. So we very often just kind of draw the decision boundary. Okay, now sometimes points are misclassified, right? You sometimes often cannot, it is not actually possible to create a decision boundary that perfectly classifies the points, because not everybody who has high blood pressure and high weight is will have had a heart attack. And so, is that okay? Right? Is that okay? And the answer is, well, it has to be okay, because there's no database that's perfect, especially when you're dealing with medical data, which is really messy. But also, we don't expect these classifiers to be perfect, right? We don't expect them to do a perfect job at classifying things. They just do the best that they can. Our job is just to create the best possible classifier. Okay, so in notation, my data set, right? What I want to do is create this function so that it predicts well, so that when I have a new point whose label I don't know, that it'll be correctly classified. So for instance, if someone has low blood pressure and low weight, my classifier is likely to predict that they won't have a heart attack, right? And I want those predictions to be correct. So I have this data set, which is all labeled. That's my training set. And then I would take my training set, create a function, and then test my function on a testing set whose labels were not used to train this function, okay? That's the whole setup of supervised classification. All right, so my training set, the notation looks like this. I usually call it S, and it's a set of these vectors, xi, yi, okay? And these xi's are vectors in Rn. And then the yi's are the plus and minus 1 labels. Just write plus or minus 1. And the labels do get more interesting for different problems, but for now, we're predicting the answers to yes or no questions. Like, is there a deer in this image, or will this medical patient get a heart attack? Right? These are yes or no questions. And I have n of these data points. That's the typical notation. Okay, so the machine learning algorithm, as I said, and you got to get this terminology right because it's confusing. So there's an algorithm and a model. The algorithm uses the data set S to create the model f of x. And the predictions are made by the model. And you'll almost always see reporters confuse these things. So reporters very often call this an algorithm. It's like an algorithm that the hospital is using to rank medical patients. It's actually a predictive model that the hospital is using to rank medical patients, but they often say algorithm. But in the true terminology, an algorithm eats the data set and spits out a model, predictive model. Okay, now this setup that I've just talked to you about, where we're predicting the answers to yes or no questions, this is used in lots of different applications. It's used for self-driving cars because we have to predict, is there a deer in an image, yes or no? Is there a car in the image, yes or no? All of these different questions are, this setup is exactly the setup that they use to design those systems. Also, things like face recognition, which is an interesting political topic that we can talk about for hours, but luckily we won't today. Also, things like handwriting recognition. Like when you go to the ATM and you deposit a check, that check has some writing on it, and that writing, each letter of that writing is recognized by a function f of x, whose job it is to classify whether or not that's a letter A, and then you have another function that's like, is this a letter B, and so on. Okay, so we have all of these functions. Oh, and the post office too. When you write an address on the back of a letter, you know that's handwriting that goes through the post office, and you have all these functions f of x that classify all those digits or letters that you wrote on your envelope. Also, things like speech recognition. Also, when you apply for a loan, when you go to get your first house, you will need a loan. You'll go to a bank, and the bank will take your credit history information and put it into a predictive model, and that predictive model is a function f of x that will spit out whether or not you're likely to default on your loan, right? And that determines whether you'll get the loan. Also, credit card fraud. So all the credit card companies have whole departments whose job it is to create classifiers for whether a transaction is fraudulent. So that's a yes or no question. Is this transaction fraudulent or not? And the plus labels are the fraudulent transactions. I do a lot of work on medical outcomes. So things like, stroke prediction, side effects of drugs. Are you going to get a bad side effect of this drug? Do you have sleep apnea? Yes or no? Will you have a seizure in the next 6 hours? And, I'll talk about that later too. Also, whether a child is in danger. There's a group in Pennsylvania that uses information about a child in their household to try to predict whether that child is in danger to see if they can offer extra services. And all of those applications that I've just mentioned follow this general setup. Okay. Do I have any questions? Okay, great. Oh, you have a question? Not yet. Okay. All right. So now machine learning, what machine learning is famous for are complicated models that no human can understand. Because usually it's not just 2 dimensions, it's like a million dimensions, and like these functions are really complicated. And so that's what the whole field is famous for. But these are like complex models where a human can't understand it, but it predicts well. Because the idea is like it's picking up on some secret information that the human can't possibly comprehend. But those aren't the kind of models that I like. I like simple models. I like things I can understand. I want to know what the model is doing. And I particularly like predictive models that are so small that you can memorize them or put them on an index card. Those are my favorite kinds of models, because then I can give them to doctors and have them use them in high stakes decisions. So yeah, so that's what I like to do. And I call this field interpretable machine learning. And it was not very popular for many years, but started to get popular recently. And as it turns out, for many data sets, especially medical data sets, you can actually create very simple models that are very, very accurate. It's really surprising that this is true. And I should tell you that the most widely used predictive models in medicine are actually simple models like the APGAR score, which is used for ranking babies right after the newborns, as well as the CHADS-2 score, which predicts stroke in patients with atrial fibrillation. These models are so tiny that you can even memorize them. So what I want to do here is I'm going to actually, there was a demo yesterday that was really spectacular. So Princess was at the library showing people kind of how these classifiers can work and how you can see them actually operating. And so I have, I'd like to ask for a very small volunteer to demonstrate some of these how these machine learning models work. Okay, so let's go to the front. And if you don't mind, could you do a demo of the machine learning tool? There you go. Here it is. Okay, so Sylvie's going to demonstrate. This is a Google product. I have no way endorsing Google on using this. Google is one of my least favorite companies. So what she's going to do is she's going to press this button. Whenever she's ready, you can go. And she's supposed to draw a lollipop, and then there's a whole bunch of classifiers in here. There's a classifier for street light, garden hose, all that kind of stuff. And then the lollipop classifier recognized what she drew as a lollipop. And so then that keep going. You just keep doing it. Right. So I want to just point out that all this stuff actually is going on behind the scenes. Like there is a broccoli classifier that's on the train. It's a function. It predicts, 1 when she draws something that's similar to a lollipop. A screwdriver? You know what a screwdriver is. Come on, you can do that. Okay. I want to also mention that for images, when you're working on images, the only technique that's working right now for images, for image classification, is neural networks. Neural networks is not my favorite technique to use for a couple of different reasons. The first reason, actually the main reason, is that it's very difficult to train neural networks. And I know the neural network people would say, no, that's not true, they're easy to train. But in my experience, they're very difficult to train because they involve non-convex optimization. But That's the only, and another reason I don't like neural networks is because they're the ones that produce complicated models that people don't understand. And so if you're not using images, if you don't have image data, then you don't actually generally need a neural network. Like there's only certain types of problems where neural networks are actually really, really give you a benefit over other types of techniques. And what I'm going to focus on for the first, for this lecture and then the two afterward, and even maybe the fourth one is models that are very simple that you can put on a slide for applications where you don't need neural networks. Because like I said, for most applications, you really don't need them. Okay, so you are good. Thank you so much for your help. You can take the outside. Got it? Good. That was the deal. She gets to keep the iPad. Uh-oh, that didn't work very well. Okay. Yeah.
So Cynthia, you put natural language in the same category as images, or do you think there are other approaches that work well?
So natural language, we're not really sure. Because if you talk to, I mean, there's some natural language processing people who are like, no, we need this big model. And some of them are like, no. I mean, for natural language generation right now, we do need a big, a big thing. But it's not really clear whether that's, I'm not completely sure about that. I think I'll leave that one up in the air. Yeah, but I can tell you that I run Duke's poetry team. So we generate automatic poetry, and we have just spent years just fighting with those neural network methods. They're so difficult to use. Okay, yeah. People also thought things like music generation would need neural networks, but we've been able to successfully generate music with something that's so much easier to deal with. That is not a neural network. Right? So it's really not, some of this stuff is really up in the air. It's not really safe. Okay, so I'm going to teach, and my goal is to teach you how to build two types of predictive models, decision trees and GANs. So this is what a decision tree looks like. This is an example of one. So this tree predicts whether or not somebody's going to be arrested based on their age and number of prior offenses and other information about their criminal history and so on, and demographics, okay? So if the person has committed more than 3 prior offenses, then we predict that they'll be arrested within 2 years of their, the 2 years of the time that it's actually data from when people filled out a particular form. So these people were already in jail filling out this questionnaire. So this is a particular population. Okay, so if they've had more than 3 prior offenses, we predict yes. If they haven't had more than 3 prior offenses, we look at their age, because age is a major factor in determining whether or not people will be arrested. Okay, so if they're above 26, we predict no arrest. If they're below 26, well, how many prior offenses have they had? If they had more than 1 prior offense, yes, predict arrest. So in other words, if they've had more than 1 prior offense and they're young, we predict yes. Otherwise, we ask if they've had juvenile crimes, not predict no arrest, if yes, predict arrest. So this is an example of a decision tree. I'm not saying you should use this in practice. There's a lot of things to consider and whether or not to use it in practice, but this is the form of the model I wanted to teach you how to construct. And then this is a GAM. So this is an additive model. And you'll see, if you're familiar with sort of statistics and regression, what you'll notice is that here all the variables are interacting with each other. There's a lot of interactions, whereas here there's none. This is a linear model in the sense that you're adding up a bunch of things. And then depending on what the score is, that gives you a prediction of positive. Yes or yes. Yeah, if you get 3 points, your probability is 50% that it'll be positive. Okay, so I want to teach you how to construct these 2 types of models. This model over here is actually a real model that we constructed with neurologists, and this is actually a machine learning model that's used in a very high stakes decision-making setting, which is predicting seizures in intensive care unit patients. And I'll tell you about that in a minute.
So for decision trees, are there always two options per stage? Can there be more than two?
There can be more than two. This particular type of decision tree only has binary split, but there can be decision trees with non-binary splits. Okay, let me tell you about this scoring system here. Okay, so this is an application that like I said, I've worked on this with neurologists. Their names are Aaron Struck and Brendan Westover, and Brooke was my student. And they explained to us that in their patients are critically ill. So these are patients who had an aneurysm maybe that burst in their brain. So this is like a hemorrhage, brain hemorrhage with blood in the patient's brain. And these patients get surgery and they're placed in the intensive care unit. And about 20% of these types of patients get seizures, and seizures lead to brain damage. And so they have these monitors, all of these patients that are measuring for the probability that the patient will have a seizure. Okay, so it's a yes or no question whether or not the patient will have a seizure. And the model that we designed for them, we called it 2 helps 2B, because the 2H is like, if the pattern has frequency 2 hertz, so 2H, ELPS, and 2 points for the B. And so the doctors can memorize this model just by knowing the name of the model. And that really helps them because they can just look at the patient, look at the EEG, and say that patient has this and this. We'll give them 2 points, and then we know what to do with the patient. So the algorithm that creates this model is very complicated, but the model itself is designed to be very simple. All right, so my goal is to teach you the basics of machine learning and teach you how to create these 2 types of models from data. Okay? And I want to get you all the way from, the beginning of the field up until the present day, what we're doing kind of in my lab on these 2 problems. Good. Interesting. Okay, how do I not have it do this? I can see what I'm doing. Okay. Okay, so before I get to how to construct these models, I need to teach you some basics about machine learning. And in particular, I need to teach you the principle of statistical learning theory called Occam's razor. Okay, all of machine learning is based on this idea of Occam's razor. Okay, so Occam was he was an English historian and a philosopher, and he knew nothing about machine learning. But he said that among hypotheses that predict equally well, we should use the one with the fewest assumptions. Okay, so that somehow abstract idea got turned into a theory that is used by machine learning people. Okay, so the idea is that the best models are simple models that fit the data well. And we have a nice image that sort of shows kind of what's going on here. Oh, that's not it. All right, so here's my data set. I am trying to predict a person's income based on the number of Business Week clicks they make. So the number of clicks on the Business Week website, right? So I have this data that looks like this, and there's lots of different ways I could fit this. Now, if I fit it like this, you probably would say, Cynthia, that doesn't look so good because it's overfitting the data, right? I'm basically memorizing all the data points and I'm not going to be able to generalize. So when I put my test set up there, the test set, it won't predict well on the test set, okay? So that's not good. I also don't want to underfit because then I'm not actually doing a good job predicting. So what I want to do is get the right balance between overfitting and underfitting, and that has to do with the simplicity of the models I'm using. So here, this is a very simple model, didn't fit the data well enough. That model is too complicated, and it overfit the data. So the idea with this special picture that I talked about is that there's a sweet spot between underfitting and overfitting. So along this axis, is model complexity. So if you have very, very complicated models, you are able to overfit the data. If you don't have complex enough models, you won't be able to overfit the data, you'll underfit it. And then what you'll see on your training set looks like this. Because the more complicated models you use, the training error will go down and down and down and down and down. Now, the interesting bit is the way the test error relates to the training error. So if you have overfitted your data set, then your test error will go up because you won't be able to generalize to the test set. Whereas if you chose a model that was very simple, then you'll generalize really well. The training and the test set performance will be very similar to each other, but neither model will perform well. So what you really want is to get to the sweet spot where your training error is low, but where you can generalize well to the test set. Okay, so this is like the key picture that you should always keep in your mind when you're thinking about machine learning. Any questions?
So usually I think the test set is much smaller than the training set, right?
No.
Oh, okay, so that's not true.
Right, that's not true. We usually think about the test set as the whole distribution of where the data is drawn from. Usually the training distribution and test distribution are assumed to be drawn from the same
Right, I know that's the
distribution.
assumption.
And so when we usually think about the test set, we usually think about the whole distribution.
Okay,
Yeah. Where were you going with that question?
okay, so what I was doing is I thought that, under my, I guess mistaken assumption that the test set is usually much smaller than the training set. But in fact, it's a much smaller sample of the underlying distribution than the training distribution. And so I'm always a little confused about how they can draw conclusions from a small test set.
Yeah, we usually think about the test set as being the whole distribution that the data are drawn from. Yeah. Okay, great.
Isn't it in practice like 10% of data set used as a test set and then maybe 90% used as a training?
You might be talking about writing a paper, but I'm talking about like real applications. So in real applications, you design the model, you launch it into the real world, and you expect it to work for quite a large number of other cases. Yeah. Yeah. Okay. So what we need is a balance between accuracy and simplicity, because in order for us to get to that sweet spot, we need models that are accurate, but they're also as simple as we can get them. So the most common machine learning methods, they choose the function f to minimize some combination of training error and complexity. So they'll try to balance between those two things. And that aims to thwart what's called the curse of dimensionality. So you may have heard about the curse of dimensionality. And the idea is that as long as you choose a model that is somehow simple enough, then you won't get killed by this very large number of dimensions you might have in your data set. Okay, so the typical way that we design models is by using algorithms that optimize something that looks like this. So it's a combination of a loss on the training data and model complexity. So we want our models to be accurate, but also to be simple. All right, and so this is exactly the principle of Occam's razor. So we want to aim for a model that is both simple and accurate. Okay, so almost all machine learning algorithms optimize something of this form. All right, and we often call the complexity term a regularization term. And it's, simplicity can be measured in many different ways. So we usually call it regularization. And different machine learning algorithms do this in different ways. Like different machine learning algorithms use different functions L for this. They use different types of functions F. So I showed you decision trees and GAMs. And then they have different regularization as well. Okay, so that's the difference between lots of different algorithms. Okay, and like neural networks do this, and boosted decision trees, if you've ever heard of that, that does something like this. So, okay. So what I'm going to do now is I'm gonna get started on teaching you decision trees so that I'll go kind of like part of the way through decision trees. And that'll be good because the next time I'll get to review that, so we'll cement it in everybody's minds. Okay. So I'll give you an example here of a decision tree, which is predicting whether or not I'm going to get stuck in traffic on my way home from work. Okay, so is it raining? Yeah, if it's raining, well, is there construction? If there's raining and construction, I'll probably get stuck in traffic. If it's raining and no construction, I will predict, no, I won't get stuck in traffic. If it's not raining, well, is it rush hour? If it's rush hour, well, is there construction? Yeah, if yes, then traffic. Okay, so you get the idea of what this is trying to do. And the question is, how do you build this from data? Okay, first of all, why trees? Why do we care about decision trees? And the answer is that they're interpretable and intuitive. They're very popular in medical applications because they mimic the way people like to reason about things. You know, if the patient has this symptom, then do this. Then if the patient has this, then do that. These models are very powerful and nonlinear. They can be as complex as you need them to be. You can adjust their complexity by looking at the depth of the tree, by looking at the number of leaves in the tree. So two of the main decision tree algorithms that people have used over the decades are both listed in the top 10 machine learning algorithms from 2008. There was a paper called Top 10 Algorithms in Data Mining, and two of them were decision tree algorithms. So this is what I'm teaching you is not a toy problem, okay? Here are some examples, kind of old examples. So from the 1980s and early 90s. So BP's gas oil system for separating gas and oil on offshore platforms. And then in that case, C4.5, which is an algorithm I will teach you about, replaced a hand-designed rule system with 2,500 rules, and it saved BP millions of dollars. Okay, and millions of dollars back then is different than millions of dollars now. Okay, also there was a decision tree algorithm that learned to fly a plane on a flight simulator by watching human experts fly the simulator. Okay, so that's why we care about trees. And the kind of classic way that people build decision trees, it's not the only way to do it, but the classical way to do it is to start from the top down. So you take your data set and then you figure out what's the best way to split the data set into two pieces so that you get the most information about the outcome.
So for the decision trees, you talked about the two particular ones. Are they specific to a particular area of interest? So there's like medicine or like, I mean, like healthcare or like access to like amenities, or do they work in any, can they like be replicated in like other areas of interest?
So the nice thing about the vast majority of machine learning algorithms is that they can be used across domains, but you wouldn't really want to use a decision tree on images because it doesn't really make any sense. You'd say, well, is the pixel in the center white? It's not really interpretable. But you could put a decision tree people have built decision trees at the end of neural networks so that you could, if you were classifying an image, you could have a decision tree that says like, is there a vertical line over here? If so, then maybe it's not an 8. Maybe the handwritten digit is not an 8. Maybe it's more likely to be a P, something like that. So the decision trees are used pretty much across the spectrum of domains. Yeah.
But for computer vision problems, is it unlikely to get away from like a neural network kind of model?
So what you would do, so, and I'm saying this because my colleague actually does this. I don't do it, but my colleague does. He actually builds a neural front end and then plops a decision tree kind of structure at the end of it. And so the neural network handles all of the kind of nitty gritty convolution-y stuff, like scanning the image and finding things and condensing it down to smaller pieces of information. And then the decision tree handles the logic at the very end, which is sort of like, okay, you see a straight line, go this way. If you see a loop on the top, go this way. So, yeah. So they can be built into neural networks for doing images, but it's not a natural direct application for them.
Do you see any easy ways to make image classification more interpretable?
I do. I may or may not have time to talk about it on Thursday or Friday, Friday. But I may talk about it also on Wednesday. Yeah. Okay. But for most data sets, for like tabular data like this kind of data, decision trees can be used across domains. Okay, so as I was saying, the typical way to construct these things is from the top down. So you would split on rain, and then you would take the subset of data that where rain was yes. So these are the subset of days that I went home where it was raining. And then I would again split it on the feature that gives you the most information about the outcome, which happened to be construction, right? So I would construct the trees from the top down. Why is this a good way to construct trees? Well, and also, so I will mention here, why is this a good way to construct trees? Part of the reason is because it continues to subdivide the data set. And so it's very computationally efficient, because once you've split on rain, maybe now you only have to deal with a fraction of the data in each piece, and then a fraction of the data even beyond that. So computationally, it's very easy to do this. You can run it on very, very large data sets. Okay, the problem is that you might overfit, because you might just keep splitting down to the bottom. So what a lot of these methods do is they try to prune the decision trees after they've fit the data. So they might like take whole part of the decision tree and just turn it into a leaf like that. Okay, or like this part turned into a leaf. Okay, so you could think to yourself, like, is this really a good way to build a tree? And it's not really clear that this is the only way to build a tree. In fact, I will argue that it is not always the best way to build a tree. But I can at least show you how this is done so that you know how these trees are usually built.
Let's say other matter, like why did you start with rain and then construction and then Friday?
Exactly. So that's what I'm going to be spending a good chunk of the next lecture on. So I chose rain because it had the most information about the outcome, which is traffic. So it's like, if I know whether it's raining, that alone is a pretty decent classifier of traffic. That's why I chose it.
I was wondering how to measure the information.
That's exactly what I'm going to do. Thank you. Good. Yeah.
So to follow up on your question, are you saying that you do some pre-analysis of the data, so to figure out the orders in which the variable should be placed?
It's not pre-analysis. It's analysis on the fly.
Okay.
So you'll when I as I go through this lecture next time, what I'm going to do is introduce the actual calculation that you're going to use to figure out which feature is the one that's split on the top, and then that's the same calculation that's used for kind of for every split. Okay, and then toward the end, I'll teach you about modern decision tree methods which optimize all of the splits at the same time. That's a much more computationally intensive procedure, but you'll get a better tree at the end of it. Okay, great. Cool. Great. So at least, like I said, at least this is fast. And this has been done since the earliest decision tree methods, which is they're stemming from the 1970s. So this is a very historical, important field that I'm teaching you about. Okay, so in the remainder of this lecture, I'm going to be using a data set that I can put on a whole slide. The data set is about predicting whether a customer is going to wait for a table at a restaurant. Okay, so here are the features. So the features are things like whether the customer who walks into the restaurant happens to have other options nearby, right? Because if they have other options nearby, maybe they don't really want to wait for a restaurant at that table, that table at that restaurant. I'm sorry. Huh. Okay. Another question. Does the customer is the customer there at the restaurant on a weekend? Because if they're on a weekend, maybe they don't really want to wait. Or maybe they really do, maybe they would be willing to wait on a weekend, but not on a weekday, okay? Does the restaurant have a waiting area or a bar? Because if it does, it might be fun to wait there. And they would just wait. Does the customer have plans just after dinner? Because if they do, probably don't want to wait. The price of the restaurant. You know, maybe the customer doesn't really want to wait for a restaurant that is really, really cheap because they would rather pay more and go get their food now. Is it raining or snowing? Maybe that influences whether the customer is willing to wait for a table at the restaurant. And then what the restaurant actually is might influence it. So I put here a bunch of restaurants here. So we have a fancy restaurant, a nice restaurant, casual and very casual. Maybe just which restaurant it is matters. Also the wait time. So when the customer walks in, they're given a wait time. And maybe that determines whether or not they're willing to wait. Maybe they don't want to wait like a super long time. And then also whether the restaurant's crowded. Like if the restaurant is not crowded at all, do you really want to wait for a table at that restaurant? Okay. And so this is the data set that we're going to be using for those calculations, that will determine the splitting criteria. So there are 12 different observations, so 12 examples. These are all the features. These are the values for all the features. And then these are the labels. So this thing is X, right? This is all the X's, and this is the Y's. Like this is whether or not they waited for the table, okay? So here, the first person, they did have other options. It was not a weekend. There's no waiting area at the restaurant. They do have plans. It's a very expensive restaurant. Wasn't raining. It was Mateo. They waited. This is a fancy one. They were told the wait time was 0 to 5 minutes. It was somewhat crowded, and then they did stay at the restaurant to wait. Okay. Do you all understand the data set? Okay, great. So here's an example of a decision tree that you can make from this data set. So here's the top split is on whether the restaurant is crowded. If it's not crowded, they won't wait. We predict that they won't wait. If it's somewhat crowded, we predict they will wait. If the restaurant is full, depends whether they have plans. If they have plans, they won't wait. If they don't have plans, well, let's figure out which restaurant it is. They're willing to wait for Mateo. They won't wait for Blue Corn, not good enough. Pizza, yes, pizza turns over very quickly. They're willing to wait. At Juju, well, it depends if it's the weekend. In the weekend, they'll wait, otherwise no.
So for the first feature, crowded, that means that they're being asked to wait, but nobody's in the restaurant, like for none?
Yeah.
Okay.
That's right.
So like what they're seeing in the restaurant is affecting whether they choose to stay or not.
Exactly. Okay, so now you can see why people like decision trees, right? They're so intuitive. They're so, yes, they're so cool. All right. So let's talk about how we do this kind of greedy tree injection. So we're going to start at the top of the tree. We're going to grow it by splitting features one by one. And to split, we're going to look at how impure the node is. And then we're going to assign leaf nodes the majority vote in the leaf. So all the data that fits into that leaf, we'll assign the majority vote as our prediction. And then at the end, we're going to go back and prune the leaves to reduce their offsetting. Okay, so now you have to decide which of these two features to use at the very top of the tree. Okay, so here's your data set. We have all 12 examples up here. Half of them are positive, half of them are negative. And the first split on the top could be either crowded or restaurant. Now, if we split on crowded, then we've had only 2 cases where there was no one in the restaurant. And in both of those 2 cases, nobody waited. If it was somewhat crowded, all 4 times that happened, people waited. Okay. And then this is for false, 2 times out of the 6. And then here's the split on restaurant. And now my question to you is, which of these 2 looks like a better split for the top of the tree? Is it crowded or is it restaurant? So who votes for restaurants? Okay, so who votes for crowded? Great. Okay, so, okay, I'm glad you're following me. Good, so this, if you see, it has absolutely no information about the label at all when you make the split, because you've got an equal number of positives and negatives in each leaf. Whereas this actually has substantial information about the label when you did that split. Okay, great. And so you can make, your splits beyond that. So how do we formalize that one type of split is better than another one? And in order to do that, I'm going to teach you a little bit about information theory, and I have about 5 minutes left. So I'm going to do this and I'll review it next time. So if you don't follow it this time, it doesn't matter. So we actually use some basic concepts from information theory to figure out how to do this tree splitting in some of the decision tree algorithms. And not all of them. Each decision tree algorithm has its own type of splitting, but for this one, we'll use a concept based in information theory. So the information from observing the occurrence of an event is the number of bits needed to encode the probability of the event. So I like to think about it as like how surprised you are that the event occurs. Because if an event has probability p, we need -2 log p bits. Okay? So it's like, well, how surprised are you that this happened? So here, a coin flip from a fair coin encodes 1 bit of information. Okay, so the probability is 1/2. So -log2 of 1/2 is 1 bit, right? So that seems pretty reasonable. That's 1 bit of information, whether it happened or not. I'm not that surprised either way. That's a tail, For an event with probability 1, we don't need any bits. I'm not surprised at all that that event happened. It was going to happen with probability 1. So it's 0 bits of information. Yeah. And so you kind of can get the idea of like how surprised you might be by looking at, log p for different probabilities. So for a fair coin, it's 1 bit. And then a biased coin landing on heads with probability 0.99 gives you that many bits of information. So this is not that interesting, right? And so you don't get that many bits of information, whereas this is quite interesting because it's happening with probability 1%. And so you get quite a lot of bits of information. All right, so if we had many events with probabilities P1 through PM, what is their mean information? Okay, so hopefully all of you have taken a probability class and you know the definition of expectation, right? The expectation looks like this. So it's the outcomes weighted by their probabilities of occurring. And so here, the information is -log2p. And so that is called the entropy, right? The expected information called entropy. All right, so if there are 2 events with probabilities p and 1 minus p, then the entropy looks like this, okay? So it's p -log2p, and then 1 minus p, -log2, 1 minus p. All right, now if the probabilities are 1/2 and 1/2, then both terms are just it's 1/2, then 1/2 here. And so the expectation is 1, right? Because it's the average of 1 and 1, okay? Whereas if you had the probabilities being very uneven, then the entropy is actually very low entropy here. So I'll just finish by just telling you why this definition of entropy matches with your sort of intuition about the word entropy, right? So when you think about entropy, you think about spilling a coffee cup, right? Like spilling your coffee and the coffee kind of goes everywhere and it's sort of flattening out, right? And so that's sort of increasing the entropy of the world, right? When you make a mess. Entropy means like it likes to spread out and be all flat, right? Whereas if you go to the beach and you see sand in its happy state, that's high entropy, okay? But if you go and you build a sand castle, you are lowering the entropy of the world because you've built that sand castle and you've lowered that entropy. So here, for instance, the probabilities are half and half. This is high entropy because everything's kind of flattening itself out, high entropy. And then here you've built the sand castle and you've taken all the sand from one part of the beach to the other. This is actually low entropy. Okay, so I'm going to keep that in mind. And next time, what I will do is kind of review this stuff. So just in case it didn't land quite well yet, hopefully it'll land well tomorrow. And then I'll talk about how we're going to use entropy to determine how to do splitting in decision trees. Okay? Good. Any final questions?
I had one question about the example that you saw for the wait time in the restaurants. So I was just wondering, in general, how important is it to have like a balanced set of labels in the data set for a decision tree, and specifically in application, say if one event is like a really bad event and we don't have as many samples, is there like a systematic way to handle that?
There is a systematic way to handle that, yeah. So if you have, there's a couple different ways to handle that. But usually what you would do is if you have one class that's more important than another class, either because that class is very small, so all of its examples are more important, or just simply because you really want to make sure you get those examples correct, is that when you create a sum over losses for the loss term, you would weight the more important examples higher. So you create a weighted sum of the losses and not just the regular sum of losses. It's a good question, yeah.
Right. So again, thank you, and we'll have a short break.